I've built 12 dedicated home STEM labs across 3 states, and here's something I learned the hard way. Understanding your setup requirements before you buy a single piece of equipment will save you hundreds of dollars and countless hours of frustration. The difference between a thriving learning space and a pile of incompatible gadgets gathering dust, it all comes down to planning. I'm Kazuki Tanaka, and today I'm walking you through the infrastructure decisions that actually matter, organized by age group and capability level.
You're listening to the STEM Lab podcast. Quick thing I should mention up front. All the research, measurements, and writing you're hearing is 100% from real people who've actually built these labs, but the voice you're hearing right now is AI generated. Just wanted to be transparent about that. If you've been with us for a while, thank you for sticking around. We really appreciate it. And if this is your first episode, welcome. Good to have you here. New episodes drop every Monday, Wednesday, and Friday, so there's always something fresh to dig into. Today, we're getting into something practical. How to actually set up a home STEM lab without wasting money on incompatible equipment. Let's get into it.
I'm not covering every toy on the market. Instead, I'm focusing on the infrastructure decisions that determine whether your investment actually builds sequential capabilities or just creates clutter. Let's start with ages 3 to 6, the foundation skills stage. For power requirements, stick with battery-operated or low-voltage USB devices, 5 volts DC maximum. The most reliable setups for early learners center on battery-powered devices. I've watched too many promising setups derailed by extension cord tangles and exposed outlets. Look for products using standard AA or AAA batteries rather than proprietary button cells. You'll spend less on replacements and reduce electronic waste. You'll need a dedicated flat surface, minimum 24 inches by 36 inches at table height. Screen-free coding toys need consistent, level surfaces for predictable operation. I measured dozens of foundation-level activities, and anything smaller than a standard placemat creates operational issues, where pieces roll off or children can't see the full activity field. Storage access is critical. Open bins within 30 inches of floor level work best. Young learners need to retrieve and return equipment independently to build ownership habits. I've tested probably 50 storage configurations. Tall shelving and closed cabinets kill engagement because retrieval requires adult intervention. Wide, shallow bins beat deep containers every time for visibility and fine motor development. Lighting requirements matter more than you'd think. Aim for 500 to 750 lux task lighting, preferably adjustable. Color-coded components and small directional arrows demand good lighting. I added under-cabinet LED strips to one family's setup and saw their 4-year-old's frustration with a sequencing activity drop noticeably. She could finally distinguish the red and orange directional cards consistently. For acoustic considerations, use carpeted or foam-matted floor surfaces. Dropped components are inevitable at this age. Hard flooring amplifies noise and damages precision parts. I installed half-inch interlocking foam tiles in my nephew's learning corner, and component breakage from drops decreased by roughly 60% over 6 months compared to his previous laminate floor setup. Plan for expansion space, about 12 to 18 square feet of adjacent floor area. As children progress through screen-free coding kits, activities expand spatially. I've seen families boxed into corner setups where a child couldn't extend a robot maze beyond 3 tiles because furniture blocked expansion, completely limiting the complexity they could explore. Confirm true screen-free operation with zero Wi-Fi or Bluetooth dependencies. Check carefully because some unplugged toys actually require companion apps for setup or advanced features. True screen-free coding toys operate completely independently, which matters for families managing screen time and for ensuring uninterrupted learning during travel or internet outages.
Durability standards at this age. Everything should be drop rated from 36 inches onto hardwood. Durability testing matters more than feature lists. I drop test everything from waist height. If components crack or electronics fail, they won't survive real-world use. Quality products tolerate repeated impacts without performance degradation. Now let's talk about ages 7 to 10, the computational thinking lab stage. Power delivery becomes serious here. You need 2 dedicated 15-amp circuits on separate breakers. Once you add coding robots with rechargeable batteries, tablets for scratch programming, and potentially entry-level 3D printers, you need reliable power distribution. I ran one family's entire setup through a single power strip and tripped the breaker twice in one afternoon, when the printer, 2 charging tablets, and a soldering station all drew simultaneously. Get a USB charging station with minimum 6 ports, 60 watts total output with USB-C power delivery support. The transition to screen-based coding means managing multiple devices. I installed an Anker PowerPort 6 in my own shop after cycling through 3 cheaper models that couldn't maintain charge rates when all ports were active. USB-C power delivery support matters because newer educational tablets charge via USB-C, and standard USB-A ports won't deliver enough wattage. Your work surface dimensions need to jump up to a 48-inch by 30-inch desk minimum, 30 inches in height. Robotics kit assembly requires spreading out components, instruction manuals, and control devices simultaneously. I measured the footprint of a typical LEGO Mindstorms intermediate build, 42 inches when the robot, laptop, and sorted components were all accessible. Anything smaller forces constant reshuffling that breaks concentration. Connectivity requirements: dual-band Wi-Fi router within 25 feet or a mesh node in the same room. Cloud-based coding platforms like Scratch and Arduino Web Editor perform poorly with weak signals. Uploads time out and project saves fail. I've troubleshooted this exact problem in 4 different home labs. Adding a mesh network node in the learning space consistently resolved the issues without requiring router relocation. Cable management becomes essential. Install a dedicated cable tray or raceway along the desk rear edge. USB cables, power adapters, and robot charging cords create tangles that damage connectors and waste time. I installed a simple wire basket under one desk and measured. Setup time for a new activity dropped from 4 to 5 minutes, untangling and finding the right cable, to under 90 seconds. This isn't cosmetic, it's operational efficiency. For tool storage, use a wall-mounted pegboard or rail system, minimum 24 inches by 36 inches. At this skill level, children need access to screwdrivers, hex keys, wire strippers, and measurement tools for robotics kit modifications. Drawer storage doesn't work. Tools disappear under manuals and components. I installed pegboard in 8 of 12 labs, and tool retrieval time essentially vanished compared to drawer-based organization. Ventilation requirements come into play if you're including soldering equipment or hot melt glue guns. You need an operable window or exhaust fan with a CFM rating of 50 or higher. I measure VOC levels in enclosed spaces during maker activities. Even lead-free solder flux creates detectable irritants. An open window provides adequate ventilation for occasional use. Dedicated exhaust becomes necessary if soldering happens weekly or more frequently. Floor protection matters. Use a polycarbonate chair mat or sacrificial plywood surface. Dropped screws, solder splatter, hot glue drips, and spilled isopropyl alcohol will damage flooring. I put a 4-foot by 5-foot polycarbonate mat under every workstation I set up. Not the thin office variety, but 1/8 inch thickness rated for hard floors. After 2 years in my own shop, it shows wear, but protected the underlying surface completely. Moving on to ages 11 to 14, the industry-standard tool integration stage. Electrical infrastructure needs to step up significantly. You need a dedicated 20-amp circuit with hospital-grade outlets. This is where 3D printer integration and powered tool use create genuine electrical demands. A quality FDM printer like the Creality Ender 3 V3 SE draws 8 to 12 amps during heat-up. Combine that with a laptop, task lighting, and auxiliary tools, and you're exceeding standard 15-amp residential circuit capacity. I've measured this directly with a kilowatt meter across multiple printers. Surge protection gets real at this level. Install whole circuit protection rated 2000 joules or higher, not power strip MOVs. Standard power strips provide minimal protection.
After I lost a printer controller board to a voltage spike despite using a surge-protected strip, I installed whole-circuit surge suppressors at the breaker panel for every lab I built. The cost difference is around $80 to $120 versus $20 to $30 for a strip, but electronics protection becomes genuine rather than theoretical. Work surface requirements expand to a 60-inch by 30-inch desk plus a separate 24-inch by 24-inch printer station. 3D printers cannot share workspace with active projects. Vibration affects print quality, and heated beds create contact hazards. I've run over 200 hours of print time in home lab environments. Printers need dedicated surfaces with at least 6 inches of clearance on all sides for filament feeding, cooling airflow, and burn protection zones.
Environmental controls become important. Maintain temperature stability between 65 and 78 degrees Fahrenheit, humidity between 30 and 50%. PLA and PETG filaments absorb moisture, causing print failures and nozzle clogs. I track this systematically. In my unheated garage shop, print failure rates jumped from 8% to nearly 40% when humidity exceeded 65% for more than 48 hours. Dedicated STEM spaces need climate consideration, not just temperature comfort. Network infrastructure works better with gigabit Ethernet connection preferred over Wi-Fi. Large Tinkercad or Fusion 360 files uploaded over Wi-Fi create frustrating delays and occasional corruption. I ran comparison testing. A 45 megabyte assembly file uploaded via gigabit Ethernet in 12 seconds versus 3 minutes 20 seconds over 2.4 gigahertz Wi-Fi. Run Cat6 cable if you're setting up a dedicated STEM room. Safety equipment isn't optional anymore. You need an ABC fire extinguisher, first aid kit, and emergency power cutoff. Hot ends reach 200 to 240 degrees Celsius, soldering irons hit 350 degrees Celsius, and lithium polymer batteries used in robotics projects present fire risks if damaged. I installed a keyed emergency shutoff switch on every lab's main power, positioned where anyone can reach it immediately. Software compatibility verification matters now too. Check OS requirements and license management carefully. Arduino IDE runs on Windows 10 and higher, Mac OS 10.12 and higher, and most Linux distributions. Fusion 360 requires Windows 10 or 11 or Mac OS 10.13 and higher with specific graphics card capabilities. I've troubleshooted 3 setups where families purchased Chromebooks for price reasons, then discovered they couldn't run the CAD software their team needed for competition robotics. Verify compatibility before committing to hardware. Expandability planning requires a USB hub, powered, 10 ports minimum, and spare desk outlet capacity. As skills progress from Arduino basics to multi-sensor robotics projects, USB device requirements explode. I counted connections during a recent VEX competition prep session. Laptop, Arduino board, 2 sensor modules, oscilloscope, logic analyzer, and phone for documentation. 7 USB devices simultaneously. Underpowered hubs cause intermittent connection failures that are maddeningly difficult to troubleshoot. Now for ages 15 and up, the pre-professional fabrication lab stage. Power infrastructure needs dual 20-amp circuits minimum GFCI protection on all outlets. At this level, setup requirements mirror professional makerspaces. You're running continuous duty equipment. 3D printers, laser cutters if budget allows, oscilloscopes, bench power supplies, and possibly CNC equipment. I measured power draw in my own shop during a typical project session, 18.5 amps across 2 circuits. Single circuit setups cannot support this load reliably.
Workspace dimensions expand to a 72-inch by 36-inch primary bench, plus a 48-inch by 24-inch assembly surface. Multi-week engineering projects require persistent setup. You can't tear down between sessions without losing progress. I've worked with probably 30 teens on competition robotics and science fair projects. The successful setups all provided enough surface area to leave projects in process while still accommodating new tasks. Anything smaller forces compromising workflow. ESD protection becomes critical. Install grounded anti-static mats on all work surfaces. Once you're working with bare PCBs and microcontroller programming, static discharge becomes a real risk. I killed an Arduino Mega with a winter-dry static discharge before implementing ESD protection consistently. Grounded mats with wrist straps aren't expensive, under $50 for a full station setup, and they eliminate a category of mysterious component failures. Professional-grade tools make a difference now. Invest in calibrated measurement equipment and precision drivers. I've used both $25 multimeters and $200 bench meters. The cheap ones drift out of calibration and provide readings accurate to maybe plus or minus 2%, which matters when you're debugging sensor circuits or power distribution. Quality hex drivers with correct tolerances prevent stripped screws in aluminum robotics components. Budget around $400 to $600 for a genuinely capable tool collection versus $100 to $150 for adequate hobbyist gear. Storage requirements shift to component organization with ESD protection. At advanced project levels, you're managing hundreds of discrete components: resistors, capacitors, sensors, connectors, fasteners. I use combination storage, small drawer organizers for passive components, labeled bins for mechanical parts, and ESD bags for ICs and programmed microcontrollers. Organization directly affects project completion rates. I've watched disorganized labs stall projects for days while students searched for a single connector type. Network and compute infrastructure requires dual monitors, minimum 16 gigabytes RAM, and a dedicated backup system. CAD work, simulation software, and large dataset processing for machine learning projects demand computing resources. I've run Fusion 360 assemblies with 200+ parts. On an 8 gigabyte system, the software becomes unusable. Dual monitors matter because you're constantly referencing documentation while working in design software. Automated backup is non-negotiable. I've seen teens lose 40+ hours of CAD work to drive failures.
Advanced ventilation needs dedicated exhaust with particulate filtration. If 3D printing occurs regularly, especially with ABS or other materials beyond PLA, ventilation requirements increase substantially. I installed a dedicated exhaust system in one teen's workshop after measuring particulate levels during extended print sessions. Concentrations exceeded EPA indoor air quality guidelines significantly in an enclosed room without active ventilation. Budget $200 to $400 for a proper inline fan and filter setup. Set up a documentation station with a camera mount, lighting rig, and a clean background surface. Pre-professional work involves portfolio building, competition documentation, and often college application materials. I set up simple documentation stations in 3 labs: a smartphone tripod mount, 2 adjustable LED panels for lighting, and a roll of white seamless paper as backdrop. The entire setup costs under $150 and transforms documentation quality from barely usable to actually showcasing the work. Before purchasing equipment or committing to a home STEM lab setup, run through this final verification checklist. Power capacity verified, circuit breaker rated capacity exceeds maximum anticipated draw by 25%. Physical dimensions measured, workspace dimensions accommodate expanded project footprints, not just packaged product dimensions. Connectivity tested, network speed measured at the workspace location under load, not just at your router. Software compatibility confirmed, operating system versions and hardware specs verified against manufacturer minimum requirements. Progressive path planned, current purchases support next stage skill development without requiring complete replacement. Storage capacity allocated, component and project storage planned before equipment arrives. Safety equipment installed, appropriate protective gear and emergency equipment accessible before first use. Ventilation assessed, air exchange measured or estimated for the activities planned. Budget realistic. Setup costs include infrastructure, power, furniture, tools, beyond just the featured products. Let me answer some frequently asked questions. What's the single most common setup requirement that families overlook? Power capacity is consistently underestimated.
Most families assume a standard power strip can handle their STEM equipment, but once you add a 3D printer, laptop, tablet charging, and task lighting, you're exceeding 15 amp circuit capacity and risking nuisance breaker trips during critical project phases. I've personally responded to this exact problem in probably half the home labs I've helped troubleshoot. The solution isn't buying a heavier-duty power strip, it's understanding your circuit's actual capacity and either distributing loads across multiple circuits or upgrading electrical infrastructure before you encounter operational failures.
Can I set up an effective STEM lab in a shared multi-purpose room, or do I need dedicated space? A shared space can work well through ages 3 to 10 with careful organization, but ages 11 and up benefit substantially from dedicated areas where projects can remain set up between sessions. I've measured this directly by tracking project completion rates, and persistent setup access correlates with 30 to 40% faster progress on multi-week builds. The key differentiator isn't the room itself, but whether work in progress can remain undisturbed. I've seen effective shared space setups using rolling carts for projects that can be wheeled aside but kept assembled. At what age do software compatibility and operating system requirements become critical factors in setup planning? Software constraints become genuine limiting factors around age 9 to 10 when children transition from standalone coding toys to platform-dependent programming environments like Scratch, Arduino IDE, or block-based robot programming. Suddenly, your hardware purchase decisions must align with software requirements that vary significantly across Windows, Mac OS, Chrome OS, and tablet platforms. I've troubleshooted this transition point repeatedly. Families purchase affordable Chromebooks only to discover they can't run the Arduino IDE or Fusion 360 software their child needs for the next skill stage. Research the complete progression path from screen-free to text-based programming before selecting computing hardware, because retrofitting is expensive and frustrating. Understanding setup requirements before you purchase equipment transforms random product acquisitions into capability-building infrastructure. I've watched both approaches play out dozens of times. Families who plan power, space, connectivity, and progression paths build momentum and sustained engagement. Those who accumulate equipment reactively hit compatibility walls, storage problems, and frustration that kills learning momentum. The checklist I've covered today isn't theoretical. Every measurement, specification, and recommendation comes from hands-on setup work across home learning environments from Seattle to Portland. Start with your child's current skill level, verify the infrastructure requirements for that age band, then look one stage ahead to understand what your setup needs to accommodate as capabilities develop. That forward planning makes the difference between a STEM toy collection and an actual progressive learning path that builds toward real engineering and scientific capabilities. That's it for this episode of the STEM Lab podcast. Thanks for listening all the way through. We drop new episodes every Monday, Wednesday, and Friday, so you won't have to wait long for the next one. If you found this helpful, it would mean a lot if you could leave us a 5-star rating and write a quick review. That's genuinely how other people find the show, and it makes a real difference. And if you haven't already, hit subscribe or follow so you get notified the second a new episode goes live. Thanks again. We'll catch you on the next one.